Hi everyone, it's James and Gigi here, and welcome to the Design Your Own Catapult at Home breakout with Engineering Tomorrow.
Before we start using the catapults, let's first start talking about where we see catapults nowadays. Can you guess any? You can see them in your history textbooks as ancient weapons, games like Angry Birds, or even simple wooden toys that you might get in a Happy Meal. Although all of these examples are catapults, you will notice that they all have different designs. Despite this, all of these were made with the same process, the engineering design process.
Perhaps this video can explain the idea a little better.
I'm gonna take a wild guess and say you've probably used the phone. And I bet you've enjoyed the benefits of a little thing we call air conditioning. You know who made those things possible? Engineers. We were just talking about engineers in our last video, people who design and build things to solve problems, and there are lots of different kinds of engineers. No matter what type of engineer you want to be though, civil, mechanical, electrical, or a kind that doesn't even exist yet, there's a series of steps that all engineers follow when they're trying to solve a problem. This process is called, wait for it, the engineering process. Makes sense to me. So what sort of steps are included in the engineering process, and why do we need it? Let's go through it step by step and discover how awesome things are made. First thing you gotta do is just define the problem. I mean, before you can solve a problem, you have to figure out what it is, right? For example, back in the 1800s, an engineer named Alexander Graham Bell was trying to come up with a simpler, cheaper way for people to communicate. Back then, the best you could do was a telegraph, which was an old-fashioned system of sending messages over electrical wires. Bell identified his problem. Communicating with people who were far away was expensive and took a lot of time. So his invention or solution to this problem was something you may have heard of. The telephone. Nice. Now, once you've figured out what problem you want to tackle, you need to do your research. You can start by just making a list of questions you have and what information you need to start answering them. You can also look around and find what other things already exist that have tried to solve this same problem. Maybe they can be improved. A good example here is the man who helped us blow stuff up. The chemist and engineer Alfred Nobel invented the explosive known as dynamite, not because he particularly enjoyed explosions, but because miners and other people who, well, needed to blow stuff up to do their jobs needed an explosive that was safer to use. So before he started on that problem, Nobel did research to see what explosives already existed, which ones worked well and which ones didn't. This takes us to step 3. Develop a solution. After your research is done, this is where you say exactly how you think you can solve the problem. And once you've thought of a good solution, you have to figure out how it'll actually work and what it will look like. So you have to design your solution. This is where you get to draw. Civil engineers always sketch out their ideas, like buildings and bridges and towers, to show what they'll look like when they're done. Gustave Eiffel designed the famous Eiffel Tower in France, and he definitely showed up on day 1 of construction knowing exactly what it was gonna look like. On to step 5, build a prototype. A prototype is just a simple model that lets you test out your design. It can be as big as the real thing's going to be, or it can be a smaller version. You just need to have a prototype so you can test it. This may be the most important step in the whole process. Engineers need to test their design to see if it works like they want it to. So, say if your building's a big tower, does it stand up? Does it stay standing up? If you're designing something with moving parts, does it work the way you want? Now take it from me, my future engineers. You might have a great idea, a really terrific solution to a really big problem. But when you get to this step, your prototype probably won't work exactly the way you want. At least, not on the first try. Most engineers test their prototypes over and over and over again. That's why a lot of time and brain power goes into the very last step, evaluating your solutions. Evaluating just means asking yourself whether things are working the way you want, or why they are, or aren't. I like to think of this step as question everything. This is when engineers review all of the facts and ask themselves questions, followed by even more questions. What worked well? Why did it work? Why didn't it work? How could it be made better? And most of the time, the answers to these questions are going to send you back several steps. Like, once you figured out why your prototype wasn't working, you'll have to design a new solution and then build it and then test it again. Sometimes engineers go through this process 4, 5, even 6 times or more. Take Willis Carrier, the inventor of modern air conditioning. He tested his prototypes for years before he figured out the design that worked the way he wanted and solved the problem he wanted to fix. Like all engineers, he failed a lot before he succeeded. And that's okay, because he learned something from every failure, which made his product even better in the end. And I, for one, am glad he kept going. So the engineering process is a series of steps that engineers, or anyone, should use when they're facing a challenge. The process is important because it allows engineers to experiment and also to fail. Both of these things give engineers a chance to go back and improve on their original idea, giving us something even better down the road. So the next time you fail at something, don't feel too bad. Think about the telephone and the air conditioner and the Eiffel Tower, and then try again.
As explained in the video, there is an iterative process when designing a product: research, design, build, test, analyze. Iteration is the concept of continuously experimenting and improving the prototype you are working with, as a means of creating a device that best accomplishes what you want. It is a key step of the engineering design process, coming after the planning and designing phases, and is followed by data collection and further iteration. And remember, the first thing you build likely won't accomplish all of your goals, and you'll have to go back for redesigning. That's why we have a design process.
So let's apply this to what we're doing today. Here's the basic design process for making a catapult.
Step 1. Define the problem or challenge. Your challenge is to build a catapult that can accurately hit a certain distance, so keep this in mind when you are designing.
Your goal today is to be able to hit a target 60 inches or 5 feet away from the base of your catapult. To do this, you will need to be able to dial into the settings of your catapult. In essence, you will need to answer the question, what settings should I use to achieve this target?
Steps 2, 3, and 4 of the engineering design process involve the design and construction of your catapult. This means you should ask yourself the questions: which materials should I use for my catapult? How should it be designed? And will I be able to build it?
Here are some examples that you can use as inspiration for your catapult. The first 3 pictures show how some people created their at-home catapult. They are different, yet and use different materials, but as long as they're able to do the job, they are just fine. Before drawing out your design, be sure to find materials that would be good for a catapult. Some popular items used are popsicle sticks, spoons, and rubber bands, but you don't need to use those if you don't want to. Get creative with it. And remember, failure is encouraged. If your catapult fails, then you just go back and redesign it. By failing, you will understand which components of your catapult don't work.
Step 5 of the engineering design process is the testing portion. At this moment, you should ask yourself the questions: how far can you make the ball go? Can you get it to hit a target like your paper wastebasket? How high can the ball go?
When testing your catapults, think about factors and responses. This idea is similar to the cause and effect concept. Factors are something you control, or independent variables, and responses are the outcome of the factors, or the dependent variable. So what is something you can change in a catapult, which is a factor, that would cause a different response, or change in distance the ball travels? Any ideas?
Here are some examples of the factors and responses of the catapults. Factors include the launch angle, height, and type of ball. Responses include distance the ball travels and the maximum height of the ball's trajectory. For our in-person labs, we use a pre-made catapult called the X-Pult. This catapult, as shown in the picture, has different settings that allow you to vary the angle you pull the catapult back, as well as the angle from which the ball releases. However, on your homemade catapult, you will probably use terminology like 1/3 of the way back or half of the way back for your pullback angle. In this testing step, determine which factors you want to vary in your testing. Observe the trajectory of the ball, meaning how far it flies, and determine how best to measure the length of the flight. Remember, your goal is to hit a certain distance away from your catapult, so the more data you collect with your catapult under different settings, the better prediction you will make.
The final step of the engineering design process we are using today is analysis, which essentially means looking at the data you collected or even going back to the design step if your current design failed.
To analyze and record your data, use Microsoft Excel software. Here is a sample data table that you can use as an example. Although you don't have to exactly measure the angle pulled as shown in the example, you can still record the angle with approximations such as 1/2 of the way or 1/3 of the way. However, one thing to notice with this example is that the height remains constant while the angle is changed. It is important to only change one factor at a time, so you know which change to your catapult causes which outcome. Be sure to remember this concept when testing your catapult too. If you don't have the ability to measure specific data, we have an exercise you can work with to learn more about modeling data in Excel to make predictions.
Since your own data may include estimates of pullback angles and some non-standard data, we provided a data table from the Xpult Catapult for you to practice creating a scatterplot using Excel. We can create a model of the Xpult machine by creating a graph of the factor that was changed to the outcome, such as the angle and distance. To create this model, highlight the data to be graphed, click the Insert tab, and then click the Scatterplot option. You will most likely get a graph like this, which you can then add titles and other elements by clicking on the Add Chart Element tab to make it look more presentable.
It would be helpful to have a trend line on your model as well, which you can get to by clicking Add Chart Element, Trend Line, then Linear. After you add all of the chart elements you want to make your graph look presentable, use your model to attempt to answer these following questions.
At what settings will your projectile land 60 inches away from the base of your catapult? At which settings will your projectile move through the point 4 inches above that 60-inch distance? What is the max distance your catapult can launch the ball? Be sure to add your answers in your movie.
For joining us and have fun with your task.